So good evening, everybody, and I really appreciate you coming in, especially given that it's the F1 weekend and road closures, and there is very lot of cool bands, music, all that happening. So there are only two things: either, so we have to make sure that our presentation is more interesting, which is quite challenging, but we'll try our best. So the topic is actually applied intelligence for Industry X.0. And I just wanted to emphasize the meaning around applied intelligence. I think a lot of time we talk about artificial intelligence, but when we were discussing the topic, we said, hey, let's talk about how the artificial intelligence is applied in a business context. So when we talk to a lot of our clients, that's what they sometimes give feedback to us that, okay, fine, AI capabilities are there, but what are we really using it for? So that is the applied intelligence side of artificial intelligence. So what we wanted to do today was we will share a few examples or applications of AI in different industries and different functions. And then later on, we will also get a little bit into the technical side in terms of what kind of deep learning, machine learning models are being used, and especially around vision. So I think these days, we've talked about IoT, we've talked about the regular sort of consumer side data in terms of transactions, billing details, etc. But that's on the consumer side. But when we look at machines, a big source of data is actually unstructured data. So it could be imaging, it could be spectrometer data, it could be satellite data. So there's a lot of vision related applications. So we want to touch a little bit on that, which we will do later. So just wanted to introduce Vulcan AI too. So I think the whole concept is, so Kamal and I actually were at Accenture, and then we have always been delivering AI as consulting projects, meaning client comes to us with a business problem. We try to figure out, how can we solve it, what data do they have, what algorithms we need to develop, and what is the output we can give to the client. And every time we do these projects, it's generally a long process because we're trying to figure out a new business problem and a way to solve it every single time. So we were getting a little bit tired and old, obviously, so we didn't want to build too many new solutions, but we thought there were a few areas where we could go really, really deep and encapsulate the domain expertise, the business process into an end-to-end application. And an example of that could be, say, demand-supply planning using AI methods. So there's a way in terms of how they do planning every year, every quarter, every week, every day. There's a way the demand planners will arrange, fleet, network, figure out where the distribution centers should be. So if you just have AI knowledge, it's not enough to actually solve that problem. You need to understand how that whole business works. So we took the combination of people who understand that business and sort of build applications with AI inside. And the benefit of doing that is that the best practice is already captured into the application. So instead of doing it as a consulting project again and again, you do it one time and then do some slight modification, and you can roll it out to many other clients. So that's what everybody is moving towards. If you look at Amazon, Microsoft, they're all building functional apps, and AI as a toolkit is becoming quite commoditized. So that's what the company is focusing on. We're based in Singapore. We're funded by EDB. We're fast ramping up. Few of the areas we focus on are around sort of machine health, asset maintenance, yield, quality control, and then also a big way on precision agriculture. And we'll talk a little bit about that shortly. This IoT thing is definitely not working. It's fine. I think it's the... So just quickly, I think the whole idea is that there are multiple problems to be solved. And the fact that today we have big data, we have AI capabilities, we have immense amount of optimization capabilities, that opens up new applications in Internet of Things, or some people call it Industry 4.0, digital enterprise. And there are 4 functions which we think are getting, I won't say disrupted, but there are huge opportunities in terms of AI helping drive business outcome. So if you look at, for instance, pricing. So like one of our clients, they are into palm oil. So they produce crude palm oil, and then they refine it into many different products. So it could be the cooking oil which you use, it could be margarine, it could be things which go into cosmetics. So each of these SKUs have a different demand in the market, and the pricing which you get in the market sometimes varies, season by season. So you have to do a few things. First, you have to figure out what is the demand going to be, say, next month. So you use AI for that. You integrate all kind of weather data, demand patterns. You predict demand for each of these SKUs. After that, you also have to figure out the supply side, because when you look at demand supply, both angles, then you figure out whether the price is going to go up or go down. Once you know that the price is going up, then you have to manage your whole production plan accordingly so that the same raw material, you're producing the right amounts of different SKUs. Once that's done, you also have to then figure out, okay, if it's this oil, what kind of packaging containers I need. Is it the 1 liter, 2 liter, 5 liter? Where are they going? The fleet, so getting the fleet cost down, how many trucks do I need? So it's a very complex system, but at each function, basically there is AI inside it. So what we're doing is, instead of building each application separately, what we've realized that a lot of data which is used is actually common. So at the bottom is what you see, what we call Vulcan super data. So it could be, one example is sort of satellite data. So we work with a lot of remote sensing satellites. And these days, and it's a huge difference. So in the earlier days, satellites were pretty expensive. So if you are CIA or a big army, then you would have access to satellites and then you can take images. If you see all these movies, you know, when some terrorists are doing something, they zoom in, they see what, so only the big players could do it. But now it's becoming actually quite democratized. So for 1 square kilometer, I think we did some math, but basically 1 hectare, you could get it for 40 cents. So 25 square kilometers is about $40. So that's, so basically in roughly $150, $200, you can get a very high resolution image of Singapore every day. And when you zoom in, you can actually identify buildings, you can identify cars, you can do a lot of things. So one example of how we are using that as AI is even in real estate. So we get these images. So if it's a country like Indonesia or a remote country where, you know, agencies like URA are not there, where you have data in terms of condos, sales, all that, you take that, you process it, you can even identify where there's a condo with a swimming pool, where is a mall, how many cars are there, so you do that. So now that satellite data has been annotated automatically using AI, and it can be converted into structured data where people can use it for other things. That's one. I think PSA and all those shipping companies now starting to use it. Commodity traders use it these days because looking at satellite images, the shape of an oil tanker is very unique. So even if you don't have AIS data, which is the satellite data for ships, you can identify based on the ship, like is it carrying crude oil, is it carrying containers, is it carrying cars? So you get an early insight into what's happening on the trading side. So there's a huge potential, you know, area around satellite data. So that's at the bottom. Then on the top, typically in any IoT platform, you will have complex event processing type of functionality, processing all the data, doing various transformations, cleaning it up. And then once that is there, there will be AI applications on top. So these are just a few examples of which I talked about, like network and fleet optimization. So one of the projects which EY did, in fact, was around all Samsung, Apple distribution in India. And the whole problem statement was that how do we get it to a particular supplier within a certain time, but at the lowest possible cost. So you basically re-simulate where should the distribution centers be, how many trucks should be, and then before making that investment, the system sort of simulates and then says, at this least cost, this is the best place to keep all the regional centers. Then there is smart factory and manufacturing, demand supply. I talked about alpha generation for trading. This is the other thing. Basically, the oil example, even in the fruit industry, basically if you know the different crops, you can look at the weather patterns, satellite images, and see any disruptions happening on the supply side, like coal. So if there are suddenly floods in mines, you can detect that, and you know coal supply is going to be disruptive, and then you take a pretty different position on your trading side. So there's a lot of money which can be made if you can tap on this data, which is not easily available to other people. It is, you can subscribe to it, but just the volume of data is huge. So you need AI to sort of process that. Yeah. So I think I will skip to this. So this is a big area, and the second speaker, Dr. Hong, will also speak about this. So in the earlier days, I think about 15, 17 years back when I started doing analytics, most of the analysis was done on consumer generated data. So if you look at StarHub, Singtel, DBS banks. So the whole objective was, if anytime you're making a transaction, be it at the ATM, credit card, whatever, it generates some data. And by looking at those behavioral patterns, you can actually figure out which segment of customer do you belong to. So what StarHub would do it is basically, are you making a lot of overseas calls? Are your calls mostly on Sunday? Is your phone prepaid? Are you topping only $5 at a time? Do you top up just after your payday? So then you categorize it. Or this could be a foreign worker because he's making calls to that. And then based on that, then you would basically sell very different kind of value-added services. So that's how it all started. But recently, I mean, the amount of data which machines are generating is a lot more than human-generated data. Machines are getting more expensive. Downtime is really expensive. If you look at SMRT, train breakdown, it's all machine-related. If you look at your car, motorcycle, the OEM would always give you some guideline. It will say, first 5,000 kilometers, you need to change oil. Every 2 weeks, you have to change the tire pressure. But the reality is it's pretty standard. It's what we call schedule-based maintenance. So you do that. But in reality, the operating environment may be very different. So you may think you're a Sebastian Vettel driving very fast, accelerating, braking hard. Your car obviously will break down sooner. So, but these days, cars and other assets have a lot of sensors. They will have vibration, temperature, a lot of these other things. And the whole concept is, can there be an AI embedded in the machine which is monitoring all these things, the way you use and you make the asset perform? Can you actually detect sooner if things are going to break? Or if you're a very light user, actually you don't need to do every 10,000 kilometers, you could stretch it. So there is this whole trade-off between spending too much on maintenance versus an expensive breakdown. So in oil and gas, the other risk is that things can go really bad. There could be a fire, there could be explosions. So all those things can happen. And there are thousands of sensors, right? So this piece of IoT is really the most critical, and this is really hot right now in the market, right? So there are two things which we do here. So one is on the health side. So Kamal, you just want to talk through the examples here? Yeah.
Sure. So I think there's two reasons why AI is right for application in this, right? One is there's a lot of data. So a typical oil and gas, let's say an LNG plant, generates about 200,000 sensors of data every minute. So there's a lot of data that you can use to train. The second is the problem is complex. So if you think of one LNG train basically producing liquefied natural gas, right? There could be hundreds of units, one after the other. So what happens at the end of the process depends on a lot of complex interactions that happens all the way to the well from which the gas is coming through. So which well is the gas coming through, how you're processing it, that results in your production, right? So there's a lot of complex interactions, and that's what AI is really good at, right? As humans, we can look at one unit, maybe 30, 40 sensor data, understand what's happening. But when you look at complicated chain of systems coming together, AI is really good. So one example of what we've done in the past, again, this is for an oil and gas refinery in the region where they're basically looking at the preheat. So preheat is basically, if you think of an oil refinery, you heat the oil, you generate different condensates out of it, right? So before that, you need to heat the oil. That's what preheat does. And as crude oil flows through it, it has something called as fouling. Basically, the pipes get things stuck on it, right? And as the fouling increases, the performance goes down. Now, again, the trade-off is I can do the maintenance every month, but then I'm bringing down the plant every month. So it's going to cost me money because I can't produce. But if I let it run forever and not do any maintenance, I would actually impact my product quality. And I'd also impact the energy that I'm putting in. So it's becoming expensive for me to run it. So again, what we did here was take the data all the way from where you're buying your crude. Is it Basra heavy crude? Is it where is the oil coming from? Properties of the oil. To what are you processing up to this preheat? And the model basically learns from all of this and tells you what is the fouling going to be the next 90 days? When should you bring this particular unit down, right? And the impact we had was we could push a few of these maintenance activities by 30, 40 days, and that's basically millions in terms of value for this client, right? So that's one example of how something that people are doing with whatever monitoring systems they have, if you bring AI into it, how does it change that, right? So there's both trade-off in terms of when do you do maintenance and what value do you bring. The other example is more specific asset prediction for valves, how do you predict when it's going to fail, and so on. But I think complexity is the biggest area of application. The other piece is not looking at it from a maintenance standpoint, but looking at it from a production standpoint. Again, how do I produce the maximum I can from this particular asset, right? How do I maximize production? So again, there could be many, many complex interactions happening, including who is operating that plant in that particular shift. So the way they operate, their philosophy could be different, their experience could be different, and therefore production is actually different. Again, similar to the previous example, it could be what is coming into the plant. What is the, in this case, if it's gas, what type of gas is coming in? Properties of the gas, how much is carbon dioxide, how much are the light hydrocarbons and so on, that impacts the production. Weather impacts production. If you're liquefying gas, if it's a hot day, your production will go down, right? So you need to make some changes to the plant to actually maximize production. Again, it's a very complex set of data that goes in. Humans try to optimize your physics-based models. The problem with physics-based models is it is a generic model. It is not something that is built for that particular plant. So the only way to build a model that is specific for that particular plant is to learn from that data. And that's what the model does. We learn from that data and then predict what are the settings you need to do, what set points, what parameters you need to change across hundreds of parameters in the plant to maximize your production, right? So again, the difference could be, you reduce a range, maybe you are producing from 30 to 50 tons of gas, and then you suddenly consistently produce above 40 tons of gas, no matter who's operating, right? So it also removes the impact of operator A versus operator B, because AI now prescribes what you should do to maximize your production.
So, I mean, one example of that is in the refining process, they use bleaching earth. So if the input oil is not very good and there is coloration in it, they would put bleaching earth in it. And it's not cheap. So what happens is when the oil comes in, there is what they call a golden recipe. So each engineer will have some golden recipe that, for every X tons, I need to put this much bleaching earth. As it processes, they will take samples every, half an hour to check for the amount of fatty acid. Then somebody will run to the lab, and then it takes another 2 hours to get the results back. And it says, okay, fatty acid is this much. And then if the fatty acid is high or coloration is still high, they need to increase the bleaching earth. But what happens is it's already 2 hours since the oil went in and you got the results back. So by the time you change it, it's already a little bit too late. So one of the things now people are doing is, because there is sensors and you already have a view of the oil quality coming in, you build a predictive model which basically says if the different set points are this, and if I put this much bleaching earth, this is the output I will get. So now what's happening is it's already optimized a little bit upfront based on the input quality. So they still do the sampling, but the variability in the output has been reduced. And just by doing that, they're saving millions of dollars. The scale is really huge.
Yeah, I think vision, as Manik was saying, is a key area from an AI perspective, right? Today, AI as a capability is probably equal or better in some cases to a human looking at an image. And you can apply it in various settings. This example is application in a manufacturing plant, right? So in any manufacturing plant, whether it's automotive assembly or in this case, ceramic tile manufacturing, you have people looking at the product as it's moving through the manufacturing process, looking at the quality, right? In case of ceramic tiles, what you use in bathrooms and so on, they look at, is there a pinhole in the tile? Is the tile chipped? And so on, right? And what happens with humans is, it moves quite fast. People make mistakes. So they're not able to catch it at the right time. And then you're going to spend time processing, spend energy processing the tile. At the end of line, you're going to throw it away, right? So what we did here was basically take a very simple sensor, a phone, right? And then bring the AI model onto the phone. So you can actually have the phone on top of the process. It records what's happening, detects which specific tiles have which specific defects, and then you can route the tile accordingly, right? High quality tiles, you could sell at a premium. Low quality tiles, you basically reject it, right? It goes to scrap, but you're not spending any additional processing on top of it. But that's just one example. I mean, any manufacturing process, whether it's car seats, I think another example which I've heard of is people using AI in automotive manufacturing, car seats. So is the seat crinkled, is the leather put properly? You can use AI to basically detect that as well.
So, this is another example, and especially in sort of resource-intensive industries where there are a lot of people, you basically need to, sometimes, clients want to, what we call is micro-supervision, basically to see whether the staff is doing the right job or not. This is generally applied in more sort of agriculture, manufacturing, that kind of a setting. So this was an example where you're supposed to spray fertilizer, and then there is a specific way of spraying fertilizer. So a lot of the worker, actually you're supposed to spread it like this, because the tree trunk is there. It's supposed to be sort of spread around it, but sometimes people may just throw it like that. So we wanted to do two things. One is and they always see it. So there are different roads in a plantation. So if it's close to the road, generally you will see from the satellites, it's quite green, it's quite nice. But as you move further away from the road, actually the tree is not very healthy. So the hypothesis of the managers was that, when you give them fertilizer, it's heavy, they walk. So initially they just put more, so they finish it, so they don't have to walk till the end. So the trees at the end are always a little bit, undernourished. And you could see that pattern everywhere. So one of the things we did was we basically put some simple $20 smart band, and we got a few things from there. So basically one is the whole motion, and then also the location. And then based on that, we could easily sort of figure out which are the areas which are under fertilized and which are the areas which are over fertilized. And both things are bad, because this company actually spends $300 million on fertilizer every year. And I think there's at least, and we found that 10% is being over fertilized, meaning you're putting more fertilizer than is required. So overall, it's all balanced, right? So if you say, okay, you need to give X tons of fertilizer, it's all being, on paper, it looks great. But the problem is the first few rows are getting over fertilized, and then those ones are under fertilized. So you're wasting fertilizer here and spoiling the soil also, and then you're losing yield behind, so which is under fertilized. So that kind of variability using variables, it's very easy to sort of track. And we are extending this concept to now sort of smart helmets. So one of the way they check whether the fruit is ready for harvest or not is a simple formula which says there are 2 loose fruit on the ground for every kg of fruit. So the workers are actually supposed to walk, take a look, but nobody does it. So they just go wherever they feel like and they get the fruit. So as a result, the fruit is sometimes overripe, it's rotten, sometimes it's underripe. Both are bad, right? So what we're now trying to do is basically have a camera on the helmet, because helmet is mandatory. And as the person is walking along, basically we'll have YOLO kind of models. You look only once. It's basically automatically scanning each loose fruit. It's scanning it, identifying it, and then storing the GPS location. And then based on that, the AI runs and then figures out which trees are now ready for harvest. And then it creates a map that, tomorrow, tree number 1, tree number 10, tree number 15, these are the ones you need to go and harvest. So if they can actually deploy it, it's a huge, huge uplift in terms of quality. Sorry, yep. So it's huge. Basically, each block is 30 hectares, right? So even if you can get the row, right, because they're actually supposed to come to the same row after 7 days. So even if you can roughly get, okay, it's this area, then they will go to that row instead of going to the other row. So it still helps. So, we were on the agri topic. This is an area where, IoT is coming in a really big way. And what we're trying to do is combine the remote sensing layer, which is satellites, and all the sensors on the ground. So what the sensors on the ground, they basically humidity, moisture on the soil, different mineral content, all those things are being measured. And then they take leaf samples. So when you take leaf samples, they go sent to the lab. How much nitrogen, potassium, phosphorus is there, you measure that. We're trying to basically, but the sensors on the ground cannot be scaled. So we're trying to build models where you can, based on satellites, detect if something is going wrong somewhere, and then you send the people exactly there. So it saves a lot of time. So the whole concept is, so these are the sort of commercial satellites I was talking about. So they're about like 450 to 650 kilometers above. They take pictures. We take pictures one time. The resolution is about 60 centimeter by 60 centimeter. Then if you want even more accurate, we basically ask them to fly drones. So when they fly drones, they capture more images. We stitch it together. And then we may find things like, okay, there is a young tree, it has died, and it needs to be replaced with a new one. You won't believe it, but basically each tree is worth 25,000 US dollar a year. That's the amount of fruit it produces. So it has a lifetime of 25 years. It's like a condo. That's the amount of money one tree produces. So if it dies, you basically just lost, and if you don't infill it, you lost a lot of money. So for them, this was really important. So we do things like blank spot detection. There is a very scientific method of, every 9 meters you're supposed to plant, and they have like 20, 30 years of research where they're trying to figure out what the planting scheme should be. So what we do is the workers plant, but then the satellite basically figures out, okay, did they plant at the right distance? Is the tree dying? And as soon as we detect something, we send somebody to fix it. So it's basically like SCDF, basically, but better. So I'll skip through this. Yep, maybe.
Yeah, so I think if you go back to what Manik started saying earlier, satellite data is becoming quite available, right? It's quite cheap, but it is in some cases difficult to process the volume of data you have, and sometimes even visually you may not be able to see something because it's not just what you see in the visual bands, just RGB, but you have 8 bands, let's say. You're looking beyond visual range, and that data comes in. And that's where AI really plays a really good role in terms of processing all of that information to tell you what is happening. So kind of our first step in this whole process is, if it's palm tree in this case, is to process the satellite image and say, where are your individual trees, right? And we are talking about, 500,000, 200,000 hectares of land being processed to identify where are your individual trees. Because they know where it should be planted, right? But a lot of things happen between ideally where it should be planted, where it is actually planted, what is actually survived, and so on and so forth. So that's the first step in terms of, before you start doing any modeling in terms of which tree is healthy, not healthy, you need to know where are the trees. So that's the first step in terms of detecting individual trees in a given satellite image. And then the next step is about the infilling piece, as Manik spoke about. So again, we use a specific processing chain that looks at convolution neural networks as the first step to identify trees. And the second step is then, it's more spatial analytics to say, what is the area where you're missing trees, right? And it has to be big enough for them to plant. So it kind of identifies any geometric shape that is plantable and tells them that these are the specific areas you need to go to and plant a tree, right? So again, the people working in the field are basically, 6th graders or 5th graders, right? So they're not really educated from that perspective. So the intent of what we're doing here is also to simplify AI, in the sense of saying a lot of processing can happen at the back end, but as a user, all I need to know is follow the GPS dot, go to the place that I need to plant, and then just plant a tree. So that's essentially, that's what will make it usable, and then usable at scale.
And then weeding is another application. So every 25 years they will clear the. So this is not the cause of the haze. I can guarantee that. I mean, we just came there yesterday from Riau. There was smoke, but generally the big plantations don't use fire to clear it. It's generally the small holders. It's true. It's not just publicity. We were there. So basically, once they clear it, what they do is they actually plant what they call LCCs. Legume cover crops. So these are legumes, but they are very rich in sort of nitrogen. So when you plant these new things, when the trees have been cut, they enrich the soil again with the nutrients. And then after 12 months, then you clean it up and then you start planting the new ones. But what happens sometimes is these weeds actually grow out of control. So even when you have planted the small trees, the trees are this big, the legume crops will go even over the trees, and they will, instead of giving back nutrients, they start, after a certain age, they start sucking I think it's like our kids, right? So I think when they're young, it's all good. After a certain time, they start taking back a lot from us. So so we detect those weeds, and then they go spray weedicide and, get rid of that. We won't do that, but for weeds, it makes sense. So that's one. And again, we're talking about, like 10,000, 20,000 workers doing this every day. So if we can detect it, it's huge. I mean, it's like 100 times the size of Singapore, or probably even more. This is a really huge scale. Health is the other thing. We'll not get into detail because it's very tree specific. But the whole idea is basically anomaly detection. So we can train it that this is what a regular profile of tree looks like. And then if we detect any pattern, automatically we highlight that. Then the people actually go on the ground and then they figure out, okay, what exactly is wrong with this tree. So sometimes it could be what they call a rhino beetle. So this beetle actually goes and eats the spear of the tree. And it's very funny. So basically, if it's a beetle, then the frond of the tree becomes like a fish shape, right? So when we work with the agronomists, those are the guys who can give us these insights, that this is what you should be looking for. So if it's a beetle, the leaf becomes of a certain size. Now what we're trying to do is, basically from 650 kilometers away, we're taking images, and the images are identifying where the trees are. Within the trees, it's basically figuring out what the leaf profile looks like and whether it looks like a fish or not. Because if it's some other bag-eating, whatever, they're different worm, it's very different. So we're even trying to distinguish between different types, so that when we send the worker there, he doesn't need to go there to investigate. He's already going with the right recipe or the right insecticide for that particular insect. So that's the level of precision AI is now helping us achieve. So this one is interesting. This is more for trading. And while we were building it, Kamal and I ourselves were joking, hey, if we know this, we should start trading already. But basically the whole idea is, so palm is mostly, Indonesia, Malaysia. It produces a lot of oil. Actually, literally everything. Unilever, P&G, ice cream, McDonald's, Softy, everything has palm oil. You may not know it, but you may be consuming palm oil. It's a huge thing. So what we're trying to do here is the same thing which we've done for health, right? Like, or insect or pesticide or some infestation. If we have that information upfront, we will know whether next month's supply will be disrupted or there will be less palm oil coming. So if you know there's less palm oil coming in, that means price is going to go up. So you can actually take positions there and make a lot of money. So but you need to spend a lot of money to actually get these images. We were doing some calculations. It's $2 million to buy images for all of Indonesia. So if somebody funds us, can definitely do that. So now we will talk a little bit about how is it actually done.
Yep. So I think there's few things happening here just to give you an idea of why did we select a particular pipeline or sequence of AI models, right? Traditionally, if you think of computer vision AI models that are out there, let's say for face detection, detecting dog versus cat and so on, they leverage hundreds of thousands or millions of images to train the model, right? In our case, we didn't want to spend that much time annotating trees, right? So you don't want to, there's a cost to annotating the data and it's expensive. So the specific pipeline or the approach we took, which was unique, was to say, can we get to a 80-90% accuracy without using any AI model, right? We're using traditional signal processing, OpenCV computer vision models to get to an 80-90% accuracy. That's like an AI or annotation in a way that tells you in an image where it thinks there are trees, right? So we're not using any AI model yet. We're just building a traditional signal processing approach to identify the trees. Once we get there, then we use an AI, whether it is CNN-based model, whether it is a segmentation model, whichever it is, to get to a 95% plus accuracy. So our first pass gets us to 80-85% accuracy with no annotation needed, right? No human involved. Then we ask humans to go and annotate where they think there is a tree and not there is a tree. But it's already quite accurate. Once we get that done, then we get to a deep learning model that then improves the accuracy to 95%, 96% plus accuracy. That's kind of a pipeline that we took purely for the reason that in these kind of very specific applications, you don't have an annotated data set out there, right? Nobody's looking at trees and saying this is palm tree, this is not a palm tree. It's a very unique application. So we had to use a specific pipeline to get to this model in 3 months, right, without spending a year annotating the data, right? So that's essentially the approach that we took. Once we get to the trees being identified, then we can go on to spatial analytics to say where is high density of trees, or there's low density of trees, where do they need to plant more trees, where do they need to go and thin the trees. Thinning, so you would assume more trees is better, but not always, because it's also crowding. So if you have too many trees near each other, they would go and cut down some trees. So it's also identifying all of those subsequent analysis, but it all is possible because you get to a 95% plus accuracy in terms of saying there is a tree and the location of the tree. It's not just the count saying in this plot of land there are 2,000 trees. That's easier. It's more difficult to say in this plot of land there are 2,000 trees and this is the specific location of each tree. Right? That's where AI can really help. I think this is a very simplified version of how we would process. Again, a lot of our processing happens in Python. Starts with loading the image, then basically identifying where there's a weed. So there are a few combinations. We look at texture of the image to say, because texture basically means where there's a weed, the texture looks very different when there's a tree and so on. So identify locations of weeds and we mask it out. Masking meaning we're not processing it any further, right? We mask it out basically. Then we do some image enhancements because essentially the way we look at the image, way an AI model looks at the image is a bit different, right? So we enhance the image to make the process a lot more accurate for the AI model. We do apply, as I was saying earlier, the first pass is there's no AI model yet. This is all traditional computer vision processing. So template matching is one approach that looks for specific shapes. So a tree looks a specific shape from the top view. So we kind of use this to detect. So you can start seeing dots emerging. Each of these dots is an individual tree, right? So we're going from the image to individual trees. And then post that, that's when we create training data sets. So we cut 70 by 70 pixels in this case, where there is a tree. And again, it's about 80-85% accurate. And then we ask humans to annotate that. And after annotation, we run a convolution neural network in this case to say where there's a tree, right? We also use faster RCNN in some cases where it's not just about where there's a tree, but also the canopy of the tree. So how big is the tree? Where is the location of the tree? So there's different sets of models that we use to identify individual trees. Once you do that, then there's a lot of health indicators that you can apply to say which tree is healthy, which tree is not healthy. Different features are more sensitive to different nutrients. So for nitrogen, we use something called as deep green chlorophyll index that tells you the nitrogen deficiency in a way and so on. So I think the process basically continues. There are lots of subsequent steps in terms of saying what deficiency do you have, and sometimes these deficiencies are also correlated. So if you have iron deficiency, you're likely to have calcium deficiency and so on, just like humans, right? I mean, when we have deficiencies, it actually has some correlations to other nutrients as well. So that's where the AI model comes together.
Yep, so I think we've already taken a lot of the next presenter's time, so we just wanted to skip through. But yeah, I mean, I'll skip this, but I think one call for help is we are hiring. So if any of you, and you can take a picture if you're interested, we are hiring data scientists, UI, IX designers, data engineers, and sort of business consultants. So if you, your students, friends, family, if they're interested, they can definitely reach out to us. All right. So we'll stop here, and we'll take a Q&A at the end.